Thank you very much. It's a pleasure to be speaking in the seminar. I know that the Institute is doing very interesting work. I've seen a bunch of it from different people affiliated with the Institute, and it's very much the kind of thing that I'm fascinated by, which are a collection of really interesting physical and chemical problems that have a deep mathematical backstory underpinning them. So I want to tell a story of that sort today. Um, it'll be partly historical and partly very modern. And I'm going to try to talk about some physics and some chemistry in a language that will be familiar to topologists. Um, so you can see some applications of topology in these things where you might not expect them. So the setup here is that we have a complicated molecule, and originally the molecule of interest was rubber. And the model for rubber was that there were some junctions, and the junctions were connected by strands of monomers. So on the left, we see a sort of structural picture of this toy molecule. And on the right, we see how it might lie in solution. I'll just rotate it around a little bit. This is all the same configuration. I'm just showing it to you from different angles so that you can see that indeed there are these arcs and they meet in threes at 4 different places. So the first model for this goes back to the papers of James and Guth in the 40s. And they made the following sort of physical argument. Suppose you took a strand of this thing and you held the endpoints fixed, and you thought about what happened to the monomers in the middle as they sort of fluctuated subject to their ends being held. So there would be some volume of space that was accessible to this intermediate strand. And it turns out that the volume is proportional to a sort of, it's like a Boltzmann distribution, a negative exponential, where the constants are the distance apart between the two endpoints of the strand. So here we see the paper of James and Guth where they're summing over squared distances between points connected by a strand. So you can rewrite that sum in the following interesting way, and this was done, I think, by Eichinger and also by Flory. You could imagine for yourself that you had a vector x, which gave you the coordinates of all the junction points. And we'll think of these as the vertices of a graph. And we'll think of the connections between junctions, the strands of monomers, as the edges of the graph. And if we make this matrix L, which is a diagonal matrix of vertex degrees in the graph, minus the adjacency matrix of the graph, that's just 1 if 2 edges are joined, 2 vertices are joined by an edge and 0 otherwise, then you can observe that L is a sort of quadratic form that separates out the difference, the squared difference between coordinates that are connected by an edge. And when Eichinger noticed that, he immediately rewrote James' potential. So he rewrote it in the following sort of formal looking way, which turns out to be really useful. He said, okay, we'll stack the X, Y, and Z coordinates of all the junction points, and we'll make a longer vector, 3 times as long. And then we'll rewrite James's potential as a quadratic form given by the Laplacian applied to this 3 times as long vector. So that works out to just making a block matrix where each of the blocks is the graph Laplacian. So a weird way to say this, but a useful one, is that the positions of the junction vertices of the graph are some random variable. And It's a vector valued random variable on R3V, 3 times the number of junctions. Its mean is 0, and its covariance matrix is supposed to be the inverse matrix of this tensor product, identity matrix tensored with L. And that's just going to be, well, the inverse of the identity matrix tensored with the inverse of the graph Laplacian. But the graph Laplacian isn't quite invertible, so we have to say the pseudo-inverse instead. So we have some complicated block matrix which gives us the covariances between coordinates. Okay, so how do you say this in Topologist? So let me try to do it. This is the way I've come to think about it. Okay, you have a graph. In topology, a graph is a simplicial complex, and it's a simplicial complex with only 0 cells and 1 cells. And we're going to do something sort of weird. We're going to take homology with coefficients in R. Okay, that's a usual thing. And we'll take cohomology, but instead of having the same coefficients in R, we'll have coefficients in R3. So the first thing you think is, am I even allowed to do that? But of course, the coefficients in cohomology just have to be, an abelian group. They don't really have to be a ring unless you're doing cup products or something, and we're not doing that yet. If you make these choices, you have spaces of chains. The 1 chains are real numbers associated to edges. The 0 chains are real numbers associated to vertices. And there's a boundary map which takes weights on edges to weights on vertices by pushing forward the weight on the edge to plus that at the head of the edge and minus that at the tail of the edge. So that's the usual boundary map in homology. The co-boundary map, as always, goes backwards. So it's going to connect cochain spaces by mapping 0 cochains to 1 cochains. Okay, so what are these cochains? Well, okay, a 0 cochain is a map from linear combinations of vertices to R3 that's determined by its values on the individual vertices, which are just the positions of the vertices in space. A 1 cochain is a map from weights on edges to R3, and that's going to give you vectors associated to each edge. These are like the displacements or the directions of those edges in the graph. That's a displacement vector between 2 junction positions, xi and xj. Of course, if you think about a graph with a lot of loops in it, there's some conditions on these displacement vectors. If I sum the displacements all the way around a loop, the sum has to vanish. One way to say that is that a cochain comes from an embedding of the graph in space if and only if it's the image under co-boundary of a set of vertex positions of a 0 cochain. But a neater way to say it is that the edges which correspond to embeddings are the 0 class in cohomology with coefficients in R3. Why the 0 class? Well, if you think about it, the 0 class is the stuff that annihilates the loop space. Well, if I evaluate one of these cochains, W, on a loop, I get the sum of displacements around that loop. If that sum of displacements is 0, the loop closes. And these displacements are compatible with at least that constraint. If the sum of displacements is not 0, then the loop doesn't close, and this set of edge displacements can't possibly correspond to a graph embedding. So if you think about it this way, what physicists and chemists call phantom network theory is for topologists the following statement in cohomology. I have a distribution on one cochains, and that pushes forward to a distribution on zero cochains. How does it push forward? Well, by the inverse of the co-boundary operator, or the pseudo-inverse, because again, it's not quite invertible. Okay, so that's interestingly weird, but here's a way to use that to make a sophisticated proof of an old theorem about phantom network theory. So this theorem is called Foster's theorem, and it's often stated as a theorem about resistor networks or something. But in phantom network theory, Foster's theorem is the following statement. If I think about embeddings of the graph that come from this multivariate normal distribution, then the expected sum of squared distances between vertices that are connected by an edge is 3 times the number of vertices minus 1. That's kind of surprising because it's a simple exact formula. Okay, so here is an easy proof if you're a topologist. The sum of squared edge lengths is the total norm of the one cochain, but that's the trace of its covariance matrix. The one cochains are a normal that's supported on some subspace of the vector space. And that standard normal's covariance matrix is just the orthogonal projection onto that subspace. The trace of a projector is the dimension of the space it projects onto. So we know that this trace is equal to the dimension of the zero class in cohomology. Now, what is the zero class in cohomology? Well, it's the annihilator of the first homology. Okay, fair enough. The dimension of this annihilator is 3 times the codimension of the first homology. And since this is a connected graph, the first homology is just equal to the Euler characteristic. Therefore, this codimension is 3 times E, the total dimension of the one chains, minus Euler characteristic. But we know that Euler characteristic is E minus V plus 1. And so substituting that in, we get the result that this dimension is 3 times V minus 1. Of course, that's Foster's theorem. So it's a very short proof if you know all this sophisticated machinery. If you don't, there are various proofs involving carefully summing and using linear maps and so forth. But what's neat about this is that from a topological point of view, you might just do this accidentally. This is something that the statement about Euler characteristic would be very obvious to you, where it might otherwise be overlooked. So, okay, back to physics and chemistry. And I will now speak in a much less abstract way. So if we go back to Eichinger's formulation of James-Guth's phantom network theory, in Eichinger's formulation, the center of mass of the configuration lies at the origin. James and Guth tended to fix a vertex somewhere, but Eichinger and in some papers, Flory like to keep the center of mass at the origin. If you do that, you can define the radius of gyration to be either the average, half the average squared distance between junctions. That's this middle definition. Or since the center of mass is at the origin, just the average squared norm of the positions. So if you're a mathematician, it's not obvious why this particular measurement of the point cloud is the important one. There are two answers I've found for that. One is it's directly measurable in experiments. And so physicists and chemists like this because you can get experimental data about it. The other answer is, as we'll see, this is in some sense the variance of the point cloud. And variance is a fundamental thing in probability. So the first thing you should know is the expectation. Well, the center of mass is at the origin. That's the expectation. The next thing to know is the variance. Okay, so what did Eichinger do next? Eichinger said, well, okay, we'd like to know as much as possible about the distribution of the radius of gyration. So the first thing to do is to compute the mean, the expected value. And he said, all right, using the fact that the center of mass is at the origin, the expected value is the expectation of the norm of the x vector. That's the scalar variance of this vector valued random variate. And the expectation of the norm is the trace of the covariance matrix. Well, this I3 tensor L plus is just 3 copies of L plus. So its trace is 3 times the trace of L plus. And the trace of L plus is related to this thing that became called the Kirchhoff index. So it was certainly known to Eichinger in the 80s. Here's the line from his paper, that the expected radius of gyration was given by 1 over the number of vertices times the trace of some matrix, the pseudo-inverse of some matrix. And from there, you can get what chemists call the contraction factor, which is the ratio of the expected radius of gyration of your graph to the expected radius of gyration of a linear polymer with the same number of monomers. So that's given by this formula, 2 over v squared minus 1 times the trace of the pseudo-inverse of the graph Laplacian. And you can see that it immediately became interesting to go out and compute traces of pseudo-inverses for various graph types. So here's a table of different polymer structures with particular calculations of the trace of the pseudo-inverse for them. These are different kind of repeating polymers. The last one is a comb polymer, which I want to talk about a little more. So if you think about this whole setup, something's interesting about the radius of gyration. The radius of gyration formula that Eichinger derived was for the radius of gyration of the junctions. Those are the x positions that we saw in this formula. But the junctions aren't the only monomers. The junctions are connected by chains of monomers. And these intermediate chain monomers on the right, they all contribute to the radius of gyration. So the question is, how do they contribute to the radius of gyration? So there's a beautiful paper from the 1960s in the Journal of Chemical Physics, it's Kurata and Fukatsu, where they took limits of contraction factors as the number of subdivisions goes to infinity. And they got some very complicated formulas using some really elegant techniques. And at least for some families of graphs, they were able to carry out their program entirely and give a closed form prediction for the limit of contraction factors. So they did a number of structures, but the one that I want to talk about just as an example is this comb polymer. It has B branches, plus 2 additional ends and a main chain. And I've dotted the edges here to indicate that we're thinking of these as very long chains of monomers. And we see that the limiting factor is this polynomial expression involving just the number of branches. Okay, so what if we don't go to the limit? What if we try to do it for a finite number of subdivisions? Okay, so I'm going to try to give some intuition first, and then I'll give the statement of the theorem, and then I'll talk a little bit about how the theorem is proved, not so much so you'll feel like you could prove it yourself, but so that you can believe that the terms that appear in the theorem are the terms that have to be there. So here we go. Imagine two junction vertices by themselves. So here are two such vertices, xi prime and xj prime, and they're connected by a strand of monomers. And I want to consider this ensemble that James and Guth thought about of paths of these monomers between these two endpoints. So here's one such path, here's two such paths, here's 5, 50, 500. And you can see that these paths are starting to fill out space between the two endpoints. And further, that this volume that the paths could be visiting seems to be centered at the point that's halfway between the two junctions. So here's the picture. If there are only a few subdivisions, then there's not that much mass in the hidden monomers. There's still quite a bit of mass at the junctions themselves. And what happens is the average is close to the radius of gyration of the vertices. That's Eichinger's formula for the expected radius of gyration. But if the paths between vertices are long and have lots of monomers, like in the picture to the middle right, then there are many different paths, a lot of space is occupied by potential paths, but the hidden monomers weigh more than the junction monomers. So it's as if the mass of the polymer was actually concentrated at the midpoints of the edges and not at the ends of the edges. So as the number of subdivisions increases, we should really be measuring something much more like the radius of gyration of the midpoints instead of the radius of gyration of the vertices. And on the right, I've drawn the same complete graph, but with its midpoint graph highlighted instead of the original graph highlighted. So the idea is, as the number of subdivisions increases, the picture gets more like this midpoint radius of gyration and less like this vertex radius of gyration on the left. And in the middle, it's, well, kind of in the middle. It interpolates between the vertex radius of gyration when there are no subdivisions to the midpoint radius of gyration as the number of subdivisions goes to infinity. Okay, that's the intuition. Now we're going to try to prove it as a theorem. So here's an idea. Suppose we have an embedding of one of these subdivided graphs. So let's just say I have this blue embedding of the subdivided graph. That is a path connecting the vertex x1 prime to x2 prime, another path connecting x2 prime to x3 prime, and a third path going back to x1 prime. Now, of course, I could view these paths as just selections from some space of paths that's really large that connects the same junction points. But then I would have to deal with infinitely many possibilities for paths going from one vertex, one junction point to the next. So here's a much smaller ensemble. I get from one junction point to the next by following a series of edge displacement vectors. Let's call them here W11, W12, W13, and W14. I could rearrange these vectors and still get from one junction point x1 prime to the same second junction point x2 prime. For instance, in this yellow path, I've done W13 first, and then I've done W14 second, and then I've done W12 third, and then I've done W11 fourth. So any rearrangement of the displacements along a subdivided edge is compatible with the same positions of the junction vertices. So here's a theorem about the rearrangements. It says a lot, but what it says is that if I have subdivisions, a subdivided graph G, and the junction positions are given by X prime, while the positions of all the monomers are given by X, I get a whole collection of embeddings coming from permutations. If I average the radius of gyration just over that finite set, I can express the average in terms of a radius of gyration of the junction positions alone plus two correction terms. I want to explain why you can express it in terms of junction positions, why the weighting function on the junction positions isn't uniform, and what the two correction terms are doing there. So here's the idea. In this subdivided picture, each edge of the original graph has been divided up into a number of smaller edges, each of which ends in a monomer. These things together partition the point cloud X, giving me the locations of all the monomers in the subdivided graph. Well, whenever a point cloud is partitioned into pieces, there's a neat formula for the radius of gyration of the entire cloud. So it depends on two things: the radii of gyration of the pieces and the distance between their midpoints. And it has this kind of really pretty formula that I've written out here. It's the average radius of gyration of the pieces, averaged according to the total mass in each piece, plus the radius of gyration of the centers of mass of all the pieces. And again, those centers of mass are weighted by the total mass of each piece. You might think, as I did initially, that, oh, it's just like you concentrated the mass at the center of mass of each group and then took the radius of gyration of that smaller point cloud. And that is a term in the answer. That's this right-hand term. But you see that if I scaled this left-hand group without changing its center of mass, I would surely change the radius of gyration of the entire cloud, but I wouldn't change any center of mass distances. So somehow the individual radii of gyration have to count too. Okay, so we have to compute radii of gyration for these sets of vertices in the middle of a subdivided edge. Those are these middle three vertices in the picture here. Here's one way to get between the ends. Here's another way corresponding to a different permutation. Here's a third way. If I wrote out all the different ways to rearrange the displacement vectors to get from one end to the other end, I would get this interesting looking lattice picture. And what's interesting about this lattice is that it's highly symmetric. If I were to write out all the points that are visited by all the rearrangements of edges getting from one end to the other, I would get this very symmetric picture. And it turns out that the average radius of gyration of the paths going from one end of this lattice to the other is controlled by two things. It's controlled by the distance from the start of the paths to the end of the paths. Well, every path has to cover that much distance. And it's controlled by how far the paths spread out from the straight line. That's determined by the radius of gyration of the edge vectors that are involved in constructing the lattice. There are also some constants, but they depend only on the number of subdivisions, not on the geometry. Now, on the other hand, we had these pictures which involved squared distances between centers of mass. So here, I'm going to be interested in taking the center of mass of these interior vertices and seeing how it depends on the permutation. So here's one tor with one center of mass. Here's another tor with another center of mass. Here's a third tor with a third center of mass. And here's the lattice again with the three centers of mass drawn in. If I draw in all the possible centers of mass for all the tors in the lattice, again, you get this very symmetric point cloud. Now, what I want to know is if I have this symmetric point cloud, and in fact, it's centered at the midpoint of the edge connecting these two junction vertices at the ends, and I have another such point cloud, what is the average squared distance between one of these blue points on the left and one of these blue points in the cloud on the right? Well, again, it depends on two things. It depends on the radius of gyration of the points on the left, the radius of gyration of the points on the right, but those in the end are determined by the radius of gyration of the corresponding edge displacement groups and the squared distance between the midpoints themselves. Again, there's a coefficient, but again, it only depends on the number of subdivisions, not on anything geometric. Okay, so how am I supposed to measure these midpoint distances? Well, there's a beautiful theorem that says whenever I have a tetrahedron in any dimensional space, I can measure the distance between the midpoints of two opposite edges in terms of the lengths of the two edges. Those are these yellow lengths here, and the squared distances between the endpoints of the edges. So these are these four blue distances here. And it turns out that the sum of the squares of the blue distances minus the sum of the squares of the yellow distances is equal to 4 times the square of the midpoint distance. All right, so midpoint distances can be written in terms of junction distances. That makes it start to sound like the midpoint radius of gyration is going to be the same as the vertex radius of gyration. After all, the midpoint radius of gyration depends on these mi prime to mj prime distances, and the vertex radius of gyration depends on these blue distances. But here's the catch. If I have a pair of junctions, and I think of the blue distance connecting them, That blue distance doesn't just occur in one midpoint-midpoint pair. It occurs, for instance, in the calculation of the distance from this midpoint on the left to all three of these midpoints on the right, and in the calculation of the distance from this other midpoint on the left to all three midpoints on the right. In general, the number of times this blue distance contributes is given by the number of edges that meet at x prime k multiplied by the number of edges that meet at x prime l. But that's a different radius of gyration. That's the radius of gyration of a weighted point cloud whose points are still at the xk prime and xl prime and so on and so forth, but with weights given by the degrees of these vertices. And there's another correction term, but look, the correction term involves lengths of edges. If I put everything together, then you can recognize the various components of the right-hand side. The degree weighting here comes from the radius of gyration of the midpoint cloud. Now, of course, the original junctions are still part of the picture. So there's a constant weighting, which is contributed by the original junction monomers. How many of those junction monomers are there? Well, along each subdivided edge, there are 2 junction monomers at the ends and n-1 junction monomers along the middle. That kind of explains this 2 over n-1 term. Then, of course, the other terms we had were, well, the sum of the squared norms of the little edge displacements. Those were part of the radii of gyration of these little edge displacements, and the sum of the squared norms of the junction-junction distances. Those were the missing terms in Euler's quadrilateral law. These are the yellow terms. Together, we get this really pretty formula, which tells you that this average of radii of gyration gives you something that's in principle much easier to compute. It only involves the positions of the junctions and some very limited information about the displacements between monomers along the chains. Okay, here's the chemical consequence of this. Suppose the monomers are distributed not according to a Gaussian distribution, but according to something more realistic, like a Leonard-Jones potential or the FENE potential, or they're a freely jointed chain. You can still take ensemble averages and use linearity of expectations to say that the expected radius of gyration of the subdivided graph, even in this more realistic setup, is the expectation of a weighted radius of gyration on the junction graph, plus the expectations of these lengths and junction-junction distances. So in some sense, this offers a correction to Eichinger's model. Eichinger would have said, well, just take the radius of gyration of the junction vertices equally weighted and forget about the intermediate monomers. This model suggests that you should not equally weight the junction monomers. You should weight them by their degree. If you like, they're sort of representing parts of the strands that meet there. So a monomer that's the meeting point of 5 or 6 strands should act as if it were heavier than a monomer that's the meeting point of only 2 strands, or the end point of 1 strand. Okay, if the distribution of bonds between individual monomers was Gaussian, you can actually evaluate the expectations on the page before. And this is the formula you get. You get an exact formula for the contraction factor. How does this exact formula go? Well, it involves a weighted graph Laplacian. Here, we take the ordinary graph Laplacian and we multiply on the left and right by diagonal matrices of weights, of course, on the individual vertices. And we take the trace of the pseudo-inverse of the weighted graph Laplacian. That trace plus a new correction term involving the number of loops in the graph, or the cycle rank, or the Euler characteristic, and another new correction term, which subtracts a constant. Now, if there are a lot of subdivisions, as in the model proposed by Kurata and Fukatsu, then n goes to infinity, this 2 over n minus 1 disappears, these 1 over 2v and 1 over v terms disappear, and you're just left with the trace of the pseudo-inverse of the degree-weighted Laplacian, 1/3 the number of loops, minus 1/6. Okay, now, how would you prove it? Again, you just need to compute the expectations of the three terms. Now, the expectation of the squared norm of the W vector, the total sum of squared norms of displacements in the subdivided graph, and the expected squared norm of the W prime vector, the sum of the squares of the junction-junction distances along strands, can be evaluated with Foster's theorem. So those are easy. To evaluate this, we really need to know how the junction vertices are distributed. And using some homological techniques, you can show that these junction vertices are distributed in a Gaussian way. From there, it follows that the expected radius of gyration is given by the trace of a pseudo-inverse of a graph Laplacian. So now we can check again against Kurata and Fukatsu's formula. And we see that if we plot our formula for the 5-branch comb polymer, we get this blue curve as the number of subdivisions increases, and it converges to their limiting formula, or their limiting value. And you can see that even for a small number of subdivisions, there's not a large difference between the two formulas. I would have more or less guessed that, but I wouldn't have known how to prove it except by working out what the finite subdivision result was. Okay, so what if there are arbitrary edge distributions? Well, then it's actually considerably harder technically. The problem really is that if you have a distribution on these subdivided edges and you condition on lying in a subspace, that's generally a hard thing to do. Probability distributions don't like to be conditioned on the occurrence of an event of probability 0. So you have to show that if the edge distributions are nice enough, the distribution of junctions converges to some phantom network theory distribution. It's sort of a conditional law of large numbers, or a conditional central limit theorem. And we're working on it, but I wouldn't say I quite have it yet. So the topologist question, the topologist version of this question is the following. Just say we fix the edge lengths. Then the cochain space has a submanifold given by a product of spheres. Those are the options for each displacement. The ones that are compatible with vertex positions are the intersection of that product of spheres with a linear subspace. So when you have a product of spheres intersecting with a linear subspace, when can you prove it's a manifold? When can you analyze its singularities? Can you compute the cohomology of that configuration space? A lot has been done, especially with polygon spaces. That's the case where the graph is a cycle in computing cohomology of this type of intersection. But I want to do something more general. It's more like a linkage space. Okay, now I think I have 3 or 4 minutes left. So maybe I just want to preview another thing that's in progress so that I can ask people who are interested in fluids and in topology a question. So, okay, here's a harder problem, and it's just about cyclic polymers. So what if we wanted to compute the expected radius of gyration over unknotted cyclic polymers? So there's a conjecture going back to the 80s that an unknotted polymer should act like a self-avoiding polymer. What this really means, I think, is that if a polymer comes close to itself often, it's likely to knot on one of those visits. So therefore, among things that come close to each other often, unknotted ones should be very rare. But most non-self-avoiding polygons come close to themselves very often. So the unknots should be much more common among the self-avoiding ones, also a very small subset of the space of polymers, of the space of cyclic polymers generally. So there are some chemical techniques for synthesizing, say, cyclic polyethylene that are more or less guaranteed to give you an unknotted result. So here's some examples of 3,000 edge unknots that we found by direct computer search. It takes a long time. At 3,000 edges, the probability of finding an unknot is about 6 in a million. So we got an ensemble of 600 of them by searching 100 million examples. Here are a few of those 600. You can see that, okay, they look bigger. And if you measure the average radius of gyration over 600 polymer ensembles, they do seem to be scaling. They do seem to be growing faster than the baseline distribution of radii of gyration. But 600 isn't a large ensemble, and we're only going up to 3,000 edges. So right now we're working on a much larger computer experiment to try to push this to 10,000 edges or even more. So here's my question for topologists and fluid dynamicists and people interested in vector field knots and vortex knots and so forth. What we did in the previous theorem was we averaged the radius of gyration over a group that acted on the space, the permutation group, and then we did the ensemble average of the group action average. So we need some group action on the space of unknots to average over. And you think you know what the group is. It's probably the diffeomorphism group. That takes unknots to unknots. So could you define some sort of integral average over the diffeomorphism group and do it, giving you a simpler thing for radius of gyration? Of course, if you could do this whole thing, then you would know the radius of gyration over unknots. But maybe there's some subgroup of the diffeomorphism group that you could use. Of course, I don't know how to restrict this to knots of n edges. So that's another interesting and hard analysis question that I would love to discuss with people if anyone has an idea how to do it. Okay, well, thank you for inviting me. These are some references. The first paper appeared in 22, and it contains a sort of generalized version of the Kurata and Fukatsu result that applies in the limit as the number of subdivisions goes to infinity. The second paper is about this permutation averaging trick, and the third, which should appear very soon on arXiv at least, and the third paper is in preparation. And of course, I'd also like to thank our funding agencies, the National Science Foundation and the Simons Foundation. So thank you very much for inviting me.